Okay, so let's move on to some free particle stuff. So free particle wave function. Oh, by the way, I wanted to say that, Ipshita told you to write up the solution for problem 1 yesterday, right? So I think Nahi is the one who's going to write it, but
I sent it to her.
Okay, but I want to make it clear that it has to be a collaboration of your group. Okay, so next time, someone else in your group has to write it up, okay? Okay, good. Okay, so let's look at the energy, the plane wave solution. So if the potential energy is 0, then our energy is p squared by 2m. And then we see that, we want to look at the momentum, eigen function. So this is P acting on psi. So P, the operator, acting on psi x of xt, giving you a number P times psi x of t. So this is a context where the caret or the hat matters. So because it's an eigenstate, let me label that eigenstate by P, the eigenvalue. Then because P, the operator is minus I h, the gradient, this can be easily solved. This equation is very easy to solve, and it's just given by some normalization factor, which I'm going to choose this to the power 3. This is a convention. Then e to the power minus I by h bar, et plus minus p dot x, okay? So now see that our Hamiltonian in this case is p squared by 2m. And because of that, see that h and p is going to commute, right? Remember that if we have 3 operators, A, B, and C, its commutator is going to be something like A times BC plus ACB, right? So using that, we see that H will commute with P. That means that this is a simultaneous eigenstate or eigenfunction of H and P. So it's P eigenvalue, psi of P, xt, 1 over square root of 2 pi h bar 3 e to the power, say, minus I by h bar e t plus minus, say, p dot x. Its energy eigenvalue is just, p squared by 2m, and its momentum eigenvalue is just p. Okay, so one of the things is that these are special kind of states. They are non-normalizable. So what do I mean by that? First, let me just talk about normalizability in the position representation. So if I take the inner product of 2 states as psi and phi, what I can do is that I can introduce between them the identity operator, okay? That doesn't change anything. And then we can write the identity operator as the position operator, in terms of the position operator like that. Sorry, let me, there should be a dx phi. So this is nothing but, the decomposition of identity, right? But now, because the eigenvalues are continuous, this is an integral instead of a sum. So, and then what we can see is that, we can then write the bracket of psi and phi as d cubed of x times psi x times x phi. But what is this? This is the wave function phi of x at some time t, which I'm not interested in right now. And this is psi as a function of x complex conjugated. So this whole thing is d cubed x. So we see that what we are calling the inner product here is what I called this thing in quantum 1 plus. It is the same inner product because this thing is equal to this thing. Okay, so, and now, this, if I take the momentum eigenvalue, eigenstate psi of p, and take the inner product with psi of p prime, then it is the orthogonality condition for this is going to be, it'll be 0. But if it is not 0, then if p and p prime are the same, then it is given by the Dirac delta function. So this is the continuous analog of the, say, the stuff that we have been seeing before. For the discrete case, this is the Kronecker delta, here is the Dirac delta function, okay? So these are things that I actually covered in the previous lecture, previous course. So I would recommend that you go back and review that, because if I have to get back into these these things in detail, it'll be a lot more work that I don't think we should go into. Okay, but you should definitely go back into these things. So you should go back and look at the arguments that led to these guys, okay? So any questions?
No, sir.
I mean, okay, so what we have established is that these things, they are they are a complete set of eigenbases for the momentum operator. Okay, and they're going to be, in the free case, E is going to be equal to p squared by 2m. Now, if we have momentum, if we have a potential energy, then this simple relationship will not be valid anymore. There would be a potential. This is called a dispersion relationship. So in the case of the presence of a potential, this dispersion relationship will be more complicated. But that doesn't mean that these things will cease to be the momentum eigenstates of these operators. It'll still be the momentum eigenstates. These things just won't be the solution to the Schrodinger equation, because now you have a potential energy term. So using that, what we can do is that, and that, E will be a more complicated function of P. So because of the linearity of the Schrodinger equation, we can now say that for the general Schrodinger equation, that is when V is not equals to 0, any arbitrary state can be written as a linear combination of these states, where now we have d cubed P times, now a coefficient, a Fourier transform coefficient, A of P, times e to the power minus I by h bar, E, which will be, of course, a function of P now, and as well as other thing, but yeah, it'll be a function of P, and then plus, but this function will be more general than this, that's what I mean, plus minus I of P dot x, okay? So this is the Fourier expansion, okay? So this is why, because of its linearity of the Schrodinger equation, we can express any wave function as a Fourier series or a Fourier integral of the momentum eigenfunctions. Okay, is that clear? Why?
I don't think it's that clear to me.
Okay, so let me rehash the argument. Okay, so suppose that our Schrodinger equation has, our Hamiltonian has both a kinetic term and a potential term, right? And these are operators.
Yeah.
Now, now I find the P is, as an operator, is a Hermitian operator. So I find its eigenfunctions, say psi of P.
Mm-hmm.
Okay? So this should be this. So, in solving this equation, finding psi of P, it doesn't matter what the V's are, right?
Yeah.
Okay. And we saw that those guys, the psi of P are given by this this plane wave solution, right?
Yes.
So now Schrodinger equation is a linear equation.
Mm-hmm.
Okay, so what it's happening is that, okay. Well, no, I mean, we don't have to go to that yet. What the other assumption that we have is the following, is that given any state, you should be able to express that state as a linear combination of the eigenstates of any Hermitian operator, right?
Yeah.
So what we are doing here is exactly that. But now the linear combination, because these states are continuous, they form a continuum, not a discrete term, okay? Not a discrete set. I mean, this discrete set can also be infinite. So here what we're doing is that we are just taking the linear combination, and integral is nothing but a linear combination, right?
Oh, I see. Yeah.
Yeah. So this is as trivial a statement as that, okay? I mean, these these guys don't even have to be solutions to the Schrodinger equation.
And so, এখানে যে 1/2 pi h per to the power 3/2, এটা কি normalization factor valid?
Yeah, this is a convention, and to motivate this, we have to actually go and look at in more detail Fourier transform properties. Yeah, but the interesting thing is that these are not assumed to be normalizable, but this is. Okay, so that means that we have to put certain constraint on these things. Okay.
Sir, I'm a little bit confused about P dot x, because in this equation it's I P dot x, but before that it was only P dot x. So was
Yeah, you're right. That should not be there.
I see. That
Yeah,
makes
good.
a lot of sense.
Yeah. Otherwise, it would be a like exponentially attenuated or exploding solution.
I see.
Okay.
Mhm.
All right. So now let's move over to possibly going to be the last thing. No, maybe not. Yeah.